Thanks for the introduction. My name is A.Chouhan and I am a PhD student at University of Bremen. My research area is numerical modeling of LPBF process. So currently we are developing a numerical model at University of Bremen that can be used to simulate the mixing of two metals. So this code will be available to public in the next few months for free. So if you think that you can use it for your studies, you can do so. So first we go through a little introduction, then we see the mathematical model of the mathematical formulation of the model, and then in the end we see some results. So multi-metal LPBF. So multi-metal basically means when you are dealing with more than one metal. So for example, you can do in situ line where you can mix different powders and process them. You can do interlayer and intralayer printing of dissimilar metals. So in this case, you can basically deposit different materials in different zones. So you can have like different properties in different zones of a part. So there are some challenges with the multi-material approach. So for example, when you are doing in situ line, you basically face the issues of macro segregation of unknown elements, which is not good for in situ line, because all we need is homogeneous mixture. So for example, here is a figure which shows which is just a cross section of a single thread. So for during this experiment, a layer of aluminum was deposited over a copper substrate and then melted with the laser. So in this figure, you can easily see the segregation of aluminum and copper in the melt pool. So the second thing is when you are doing interlayer and interlayer printing, in the interfacial jewel, you basically see defects like cracks and pores because of difference in thermophysical properties of two metals. So our idea was to develop a numerical model that can simulate the complex physical phenomena that are occurring in the interfacial zone, so we can get an idea about the homogeneity of the mixing, and also we can simulate the formation of defects with this model. So next I will show you the flowchart of the model. So basically you have some inputs like laser properties, powder properties, metal properties, and in our numerical model, so we basically use equations for mass conservation, momentum conservation, species conservation, energy conservation using the BF approach, and we can input the powder information using a DEM model, and we can include the physics of Marconi and ripple pressures, and then our model basically calculates the heat flux using a ray tracing approach, which is more closer to reality. And in the output, you get information like thermal history, concentration mappings, and velocity fields. You can see the mixing of different metals, and eventually you can also see the formation mechanism of different defects like lack of fusion, intertag, and chemical porosities. So in the next slide, I'll show you the physical phenomena that we have included in our model. So here is a schematic sketch of laser moving from left to right. So as the laser moves, it interacts with the powder and the substrate and melts them. So there is the physics of melting and solidification. There are losses due to convection, radiation, and evaporation. There are convection heat transfer. And if you look at the melt pool, there are surface tension, Marconi, and ripple pressure driven flows. And when the laser interacts with the powder layer and with the melt pool, there are internal deflections inside the powder layer and also inside the melt pool. So during the solidification, there is microstructure evolution. So right now, in this current model, we have included only these physics. For microstructure evolution, we are currently working on a different phase-field model, which is basically a decoupling between this thermofluidic model and phase-field model. So there you can import the data like temperature histories and other things from your thermofluidic model and import it into the phase-field model, where you can actually see the evolution of grains for dendrites. So the governing questions. So basically we are having 5 governing questions. So the first governing equation is the BF equation. So basically, if you look at the simulation domain, we have 2 phases. One is the gas phase and the other is metal phase. So the purpose of this equation is to capture each phase. So with this equation, we can actually capture gas phase, metal phase, and the interface in between them. So the second equation is the species conservation equation. So right now we are dealing with two metals. So this equation is used to track each metal phase and also see the mixing during the melting. So if the laser interacts with the melt pool, there is formation of a melt pool, and there are flows inside the melt pool and inside the gas. So to track the flows, we have this momentum conservation equation. So there are several source terms in this equation, for like natural convection, momentum sink term, and a source term for interfacial forces that accounts for equal pressure, surface tension, and Bernoulli convection. So this is a general continuity equation for laminar and incompressible flows. The next equation is the energy preservation equation. So we are using this equation to calculate the temperature relation, and there are some source terms like for latent heat absorption and evaluation. We are encountering the losses from the melt pool using this source term. So it's like evaporation losses, radiation losses, and convection losses. So in that there is a source term for laser reflux. So we are calculating this source term using a ray tracing algorithm. So basically in the ray tracing algorithm, you discretize your laser ray into a number of subrays, and you calculate the interaction of each ray with the metal interface and with the physics with the phenomena using the Fresnel absorption here. So in the next slide, I'll show how this model works. So if you are interested, yeah, you can go to this URL. So this is a preprint of our current work. So from there you can get link to download this model. So first we have some DM simulation to get the particles position, and after running this DM simulation, we actually have the spatial information of the particles. Then we can import this information to our CFT model. So here in this case, for example, I have imported the aluminum powder over copper substrate. So after importing, we can run our thermofluidic simulation. So yeah, on the right hand side, so there are two views are shown. So basically, so it's a single track simulation. So a laser will move from left to right. So, and on the right hand side here, you will see how the different metals are mixing. So we'll see the concentration maps on the right hand side, and on the on the left hand side. On the right hand side, you will see how the temperatures are evolving when the laser moves from point A to point B.
Maybe you have to click with a pointer in the animation.
Yeah, right. Just yeah. No, this side. So, so when the laser moves, so it basically interacts with the power particles and the melt pool. So you can actually see the internal reflection inside the powder layer and the multiple reflection inside the keyholes. So in this figure, you can actually see the mixing of these two different metals. So on the top there is aluminum, and on the bottom there is copper, and here you can see the formation of mixed phases. So this data is coming from the ray tracing algorithm. So when the laser moves from point A to point B, this algorithm can also use the data about how much energy is absorbed by the metal. So when the laser moves from point A to point B, we can calculate the amount of energy that is absorbed by the material. So if you see, because of multiple reflections, the energy that is absorbed by the material is quite high. So the base metal has an absorptivity around like 10%, but due to multiple reflection, it goes up to like 60%. So yeah, this is the first study that we have performed with our model. So we are basically seeing the effect of energy density on the track homogeneities. So to perform this simulation, we have used aluminum powder over copper and melt them at different energy densities by varying the scanning speed. So here you are seeing when the laser interacts with the material. So here in this case you can see the formation of a keyhole because of high amount of ripple pressure. So when the ripple pressure forms or keyhole forms, the copper from the bottom starts migrating towards the top face, towards the top area, and mixes there with the aluminum. The thing that you have to notice here is the shape and size of the melt pool. So in this particular case of aluminum copper, the size of the melt pool is like very small and very sharp. It's not very long. So the evolving concentrations doesn't have enough time to redistribute themselves in the melt pool. So if you look at the tray, it's like very inhomogeneous. So next thing we wanted to do is to quantify this inhomogeneity. So for that we have defined a mixing index. So based on the values of mixing index, we can say, okay, if the type is completely homogeneous or inhomogeneous. So if the mixing index is the value 0, it means it's completely homogeneous, and if mixing index is value 1, it means it's completely homogeneous. Then we protect the values of mixing index with different scanning speeds. So here you can see at high scanning speed, so basically you have a low energy density, that means low ripple pressures in thermal convection, so that leads to less steaming effect in the melt pool, and that leads to more homogeneous state, which means high rate mixing index. But at smaller scanning speed, at higher energy density, the value of mixing index goes down. So the next thing that we wanted to see is the effect of remelting on the track inhomogeneity. So for this simulation, we just remelted the track again and calculated the values of mixing index. So here you can see that after remelting, the values of mixing index are going down. So that means that remelting improves the homogeneity of the track. So this is basically happening because remelting introduces a steering effect in the melt pool, which produces more homogeneous. So in the second study, so we basically wanted to simulate the formation of different defects during multi-metal LPBF. So to perform these simulations, we chose two different metals like materials. One is the aluminum alloy and the other is titanium alloy, and we decided to go with three different powder configurations. So in powder configuration A, there is 100% aluminum alloy over substrate of aluminum alloy. And in the case B, there is a mixture of aluminum alloy and titanium alloy. In the case C, there is 100% titanium alloy. Then we melted these powder mixtures at two different energy densities. So one is low energy density and high energy density. First, I will show you the results of low energy density. So when you melt this mixture at low energy density, you will see the formation of liquid fusion. This is basically happening because aluminum alloy has very high thermal conductivity and it has very less absorption, so it absorbs very low amount of energy and can distribute more amount of energy towards the surrounding. So in this case, the formed melt pool is very small. There is not enough wetting between the melt pool and the substrate, and you see the lack of fusion effects. But as soon as you start adding titanium in it, the titanium has more absorption and less thermal conductivity. So that means the temperature of the melt pool begins to rise, and which is a bigger melt pool. So in this case, you can see good wetting between the deposited layer and the substrate, and you see no lack of fusion defects. The same thing happens with the case C. In this case, 100% titanium, so the formed melt pool is quite big, and there is no lack of fusion defects. So the next thing we wanted to see is how this different powder configuration reacts at high energy density. So to perform the solution, so in the case A, you can see that in this case the energy is sufficient enough to melt aluminum. So there is a quite big melt pool and there are no lack of fusion defects. But when you add titanium, so you will start to see the formation of keyhole, and keyhole is basically instability. So when the keyhole collapses, there are formation of keyhole porosities. So in the case C, you can even see the bigger keyhole porosities that are forming. So the next thing we wanted to see how this powder mixture reacts at during multi-layer deposition. So to do that, we deposited another layer of powder over the first and melted it laser. So in the first case, you can see the formation of intra-layer porosities because aluminum alloy is the formed melt pool in the first case is very small at low energy density. But as you add titanium alloy, the multiple gets bigger and you won't see any kind of defects in these two cases. So at high energy density, you can see that there are no defects, but the thing that one can notice here is the formation of keyhole. So this is basically happening because after the first scan, the temperature in the substrate are quite high, and this leads to a formation of keyhole. So here you can see, in this case, the keyholes are, it's even bigger, which leads to more keyhole porosities. So the last thing I want to show is the multi-track simulation. So to do this simulation, we have to consider another track, just related to the first track with the edge spacing of 18 micrometers. So in the first case, you can see it's pure aluminum and at low energy density. So the foam melt pool width is very small. So there are unmelted particles between these two tracks, which that leads to intertrack porosities. But in the KSP and KC, since the melt pool is quite big, you won't see any kind of defects. So with this, I would like to conclude my talk. So we have developed a AAMS22 model for multi-material LPBF. You can download this model using this URL if you are interested, and the model can take the effects of the money equal pressure dual flows. You can actually simulate multiple reflections inside the powder bed and inside the keyhole using the Peterson algorithm. You can actually see the track and homogeneity, and we can also simulate the defects like lack of fuse and keyhole porosities using this model. So thank you. So,